Now everyone, let's say their social security numbers at the same time.
You should say it. It's recording now. All right. I'll have annotate open. You should be able to see me when I do this. So I'll have a low. That's a little low DPI for me. All right, there we go. So, all right, so we've begun. So this is the practice test. So let's start going through and explain what's up. So as you said, yeah, first one is straight false. Oh, that's ugly. First one's false. And it's simply the formula for amplifier power gain is 10 log. Well, 10 log power gain itself, AP, is denoted as AV, which is voltage gain, times AI, which is current gain. So if you were to write out the formula for amplifier power gain in decibels, which is what this is, it would be 10 log times AV, well, 10 log parentheses AV times AI parenthesis, and that will yield you your power gain in decibels. And that's the formula. This one is also super sus because it's 20 log VLV, and this is simply the decibel gain in voltage. It has nothing to do with power. This gets you one aspect. All right, down here, amplifier efficiency is defined as how accurately the output signal follows the input signal. When I read this one, I don't know if we saw this one directly. Did anyone remember seeing this specific one in class at all?
I don't.
Yeah, I don't really either. So when I think of efficiency, I normally think of how little energy do you waste doing your thing. So
because I think the formula for it is the load over like the DC power input times 100, right? And that gives you your amplifier efficiency.
Something like that. I know in the homework one, we did a problem with efficiency. So I have my homework right here. Let's see if I can find it readily. There's one thing where we had to find efficiency, I think.
Yeah, it's in like the first chapter.
Yeah, it's in chapter 1.
It's like halfway through, I believe. That helps.
Yeah, okay, so I found it. It's efficiency is equal to P load over PDC times 100.
So P, like the power that load receives, so power out over the power that is fed to the amplifier.
Yeah, from like your positive and negative like DC power, like from like the VEE
and then times 100. Yeah, so amplifier efficiency is expressed as a percentage. That makes sense. And we have the formula for it. Now the question is it defined as how accurately the output signal follows the input signal? So if efficiency is defined as the power, I don't think follows is the right term. Wouldn't follow simply be, you modify the signal and then it looks similar? I don't think that's part of efficiency. If efficiency focuses only on power and that's it, then it probably doesn't have anything to do with following here. So yeah, I would guess that this is false, most likely. Hopefully he'll release answers to this before exam.
Yeah, because to me it makes sense. Like basically what you want to see at the output, like if you're saying like, looking at the output of an amplifier, the voltage should be like the same. You should be seeing kind of like the same wavelength, more or less, just, a larger magnitude.
Yeah. Follows input. Yeah. All right.
And then I'll look and see, and I have my textbook right here, so I'll look and see if there's like any of those summary questions in the back of chapter 1.
Summaries are pretty good. If you're gonna study for the multiple choice for these things, reading the summaries of chapter 1 and 2 is basically a banger.
Mm-hmm.
It'll straight up cover almost all of it. All right. I found something on the output signal following the input signal. As the amplifier's output signal is taken from across the emitter load, this type of transistor configuration is also known as emitter follower circuit, as the emitter output follows or tracks any voltage changes in the base. Yeah, so this has nothing to do with efficiency. Amplifier efficiency has an equation. It does not have, I mean, you could define it as don't lose power, but either way.
I feel like with these, if you're not for sure it's right, false is the best way to go, because most things are going to be to the T. I think, yeah, it's the next one that kind of has this tricky bit in there.
Yeah, so this next one, true and false. So this one's actually, I'm pretty sure if I turn off that, pretty sure this one, oh, they follow me? Beautiful. Nope, wrong one. This one. Yeah, ideal amplifier characteristics, it's all here. So let's go down here. Yeah, so we have true, false. The ideal operational amplifier has the following characteristics: infinite output resistance, 0 input resistance, finite gain, and an infinite bandwidth. I think these are flipped, aren't they?
Well, I know at least it's false based on the finite gain, because I think it should be infinite gain.
The infinite bandwidth I know is correct, because I looked for I went through the lectures for the bandwidth, and the bandwidth is basically like this is the frequencies where the gain is maximized.
You want it to work everywhere.
And so yeah, exactly. So if you want your frequencies to be any frequency you want, if it's an ideal perfect world, so that needs to be infinite. Now with the resistance and the input, okay, so like think of it, if you want infinite gain, you want your output resistance, I think.
It makes sense to be 0.
Yeah. Be infinite. And your input to be 0. So it's like all the power that is coming into the op amp or is not getting reduced at all. And then inside of it, you're just making a bunch of gain.
So well, I think you do want the infinite input resistance, because that's what reduces your like VN to, or your current N to 0, right? Going into the op amp.
Yeah, so I think that's why I said I think these are flipped.
I think that's right. They're summarized in the textbook, like the 5 in chapter 2, like the 5 assumptions to make for an ideal op amp. They're in table 2.1 at the top of page 62. So as stated in the book, the 5 characteristics are infinite input impedance, 0 output impedance, 0 common mode gain / infinite common mode rejection, infinite open loop gain, and then infinite bandwidth.
So
they are swaps. Okay.
Yeah, so other Ethan posted in the chat. So from Google, operational amplifier, the ideal op amp is an amplifier with infinite input. So look at this, we can immediately say, oof, false. But infinite input, infinite open loop gain, 0 output resistance, infinite bandwidth, and 0 noise. Noise isn't addressed here, but we can already tell that this is false simply because it has 0 input resistance when we want infinite input resistance. And I remember correctly, he explained that in like one of the first lectures as showing how like technically there's inside the op amp, there is like a short, like there's like open circuit, which is supposed to be infinite. With regards to the 2 leads, like they don't interact with each other theoretically.
Yeah, I was gonna say, I think it's like open circuit between like terminals 1 and 2.
Yeah, so this is another false. He loves false, I suppose. Then we have true, false. The operational amplifier rail voltage is providing DC power to the amplifier, provides saturation limits for the amplifier, or for the amplitudes of the amplifier output voltage. So I think this is true because the amplifier can only reach maximum peaks is how much you supply it from those power rail pins. We don't deal with the power rail pins all that often because they're rarely ever drawn, because we just assume that it's ideal, but real ones, they're not ideal. So if you're powering the op amp and you reach your limit and you're drawing the maximum power from your positive negative supplies, then you can't do anything more. It just stops and you'll just have a DC voltage if you keep going higher.
Yeah, I think I would say that one's true as well, because yeah, you're kind of like, you know, your limits on
it's like
everything you can do is that.
Yeah, so you have, here's your upper limit, and then you're doing sine waves, you're having fun, and then you try and go higher and it's just gonna follow. It won't be able to do this. This is impossible because you're trying to draw energy from nothing.
Yeah, and I think that's shown in the book in chapter 1 with like that graph that has the projection.
Yeah, where it has like the line of what theoretically the linear different, like how high up the line goes based upon how much input voltage. I thought that was mostly talking about input voltage though, with controlling the saturation level.
Yeah, it's right here. Operational amplifier rail voltage is providing deep power are there for output voltage here. Obviously, if you were dealing with like a different type of amplifier, there are different rules with what matters, but this is a voltage amplifier.
Mhm.
All right, true, false. An ideal operational amplifier has 0 common mode gain. Isn't that yes?
Yeah.
That's what I got. It's true.
Yeah, that's a
Yeah.
true. Straight from the book.
Basically, like if V1 and V2 will never be equal to one another, is my understanding what that basically means.
So common mode will
Mhm.
infinitely reject them if they're the same.
Yeah.
And in other words, it will have infinite gain if they're different. So this is just a way of just saying it's an ideal amp again because it's got the infinite gain.
Yeah, and that's kind of like if you look at the equation, like with an ideal amp, you have, the basic equation is V out equals A times V2 minus V1. Well, if V1, V2 are equal, that's 0.
Yeah.
0. So you aren't amplifying anything.
We have true, false. A good example of a common mode signal is noise. What would we define as a common mode signal? I don't think noise is a good example of anything, first off, but it might be here, depending on the definition of common mode signal. So does anyone recognize that?
I don't, but let me look it up and see if.
I'm gonna look it up as well in the textbook.
Well, looks like noise counts, so wild. Wild. Understanding common mode signals. Cables and noise. Noise signals can appear in a cable and as a result of capacitive coupling nearby. Yeah, so I guess common mode signals are just signals that'll show up wherever, not necessarily something you're gearing towards or you want to appear in your circuit.
Yeah,
but you
I think
can't
that
really
one's
stop it.
true.
Yeah, this one is true. So noise is factored into the definition of common mode signal. So that's that. All right, now we have true or false. There are 2 types of input terminals for the operational amplifier. The inverting and difference. I know the inverting input, but is the other one called difference? I feel like
No,
that's,
it's
No.
just
No, it's the
non-inverting.
non-inverting.
yeah, that's stupid. I knew that was gonna be that's false right off the bat, just because that difference is not the name of one of the terminals. 8, true, false. Voltage gain in decibels is 10. Nope.
The 10
This-
is the big boy.
So 10 log only shows up when you're calculating power gain in decibels.
Yeah.
And since there's a 10 here coupled with voltage gain, then you'll automatically know that this is a no-no. Voltage gain and current gain are calculated with the formula 20 log V out V in for voltage gain, 20 log I out I in current gain.
I
And
think it's
power-
crazy that 2 of these points you can find specifically from his authorized equation sheet.
Yes,
Yeah.
It's fantastic.
great. I'm very excited for the authorized equation sheet. Yeah. Then we have, True.
You're doing air quotes, right?
I suppose,
Well, I guess it's a given you can at least get a 2 on the test.
easy
That
Nice.
makes it better.
All right, then we have number 9, true, false. A voltage follower is a unity gain amplifier. Is it?
I
Let's
don't
find out.
know.
I forget. I
It's
remember we
about-
heard about that.
Yeah, he has like slides where he just defines all the amplifiers.
I thought it was true, but I don't fully. I remember seeing it, but I don't remember exactly what he said about it.
Okay, so a unity gain amplifier is defined as an amplifier that doesn't amplify, aka its gain is simply like 1. So its a value for AVAI or whatever is just 1. So a voltage follower, does the follower simply pass a signal? If so, then it should count as a unity gain amplifier.
Was that in chapter 1? I think there was like a little.
If I had to take a wild guess, I'm pretty sure this is describing a type of buffer.
Yeah.
Yeah.
I think that, yeah,
I
that's
think
true
chapter
then.
1 where there's like the cascaded amplifiers.
All right. So what did you say again about the unity gain amplifier gain? Like, is it negative?
A unity gain amplifier is defined as an amplifier with a gain of +1, just 1.
Okay, just 1.
Yeah, so it just passes signals, which is why I just defined it as a type of buffer. Yeah, a voltage follower is summarily defined as a unity gain non-inverting buffer. voltage followers are in fact unity gain amplifiers. I'm pretty sure if you ever see the word follower, assume it's a buffer, and if it's a buffer, assume it is a unity gain amplifier. Then we have number 10, true, false. Negative feedback is applied to operational amplifiers to control the amount of gain the amplifier will provide. So negative feedback is applied to an operational amplifier to control the amount of gain that the amplifier will provide. I'm pretty sure that is, because if it's because what is it? An ideal amplifier has infinite open loop gain. So closed loop, or what is it? Closed loop or negative feedback or whatever would allow you to control and prevent it from just being infinite. Because as we saw earlier up here, an amplifier that's just infinite is useless because it's not possible. So we need some type of control architecture. So I think negative feedback is applied to limit it. Now the question is that true?
No, the question is it going to be positive feedback?
What was it saying? Negative feedback is applied to an operational amplifier to control the amount of gain. So is it positive feedback instead?
That's the question.
No, I think it's negative feedback, or like that's how the amplifiers are typically drawn, because it's feeding back to the negative terminal.
Yes.
Whereas if you had it from like terminal 2, you know, that the feedback loop that runs from the output back to the input. So if that was going from the output back to terminal 2, that would be positive feedback. Negative feedback is what's going to terminal 1.
Yeah, so
Okay.
I
It probably is negative then.
yeah, so I'm pretty sure. So I had my rationale for why I'm pretty sure negative feedback's the right term and everything. And after looking into it, it is in fact negative feedback. So this is a true statement. We use negative feedback as a control condition.
So what is it exactly asking? Is it if negative feedback is applied? Is the question whether or not it's actually negative feedback that does this, or
it is? I don't think there is a such thing as positive feedback.
No, I saw like the textbook reading through it. It's like positive feedback is basically just going from the output terminal to the positive terminal.
So it goes to the the other one. So there is one
to terminal 2 instead of 1.
Nuts.
But I guess I'm asking is the question about whether it's negative feedback, or is the question about whether it controls the gain?
Well, if you were to read this question, like it's supposed to be asking about whether or not it controls the gain.
That's what
I'm pretty sure regardless of the feedback type, regardless of how it's being used, it'll still control your gain, just in a different way.
Because I remember now he had an analogy of, if you have a ideal amplifier with no feedback, you have a horse without reins.
Yeah, it's talking about the horse.
Crazy, and
yeah,
you're just gonna waste power.
Never gonna forget about the horse.
That was a good analogy.
It was a good analogy, but he went on for the horse for about 5 minutes, and it was really funny.
Well, that's when you take the video and turn it to 1.5 times speed.
I suppose that works. All right, so this is
all 1.5 is too slow.
So this is all of the true/false questions. So real quick on a piece of paper, I'm just going to write them all down, even though they're on video. So I'm just going to do FFFT. Because afterwards, I'm going to work these problems as we go. And if we have a solution that we have some degree of confidence in, I'll scan it and post the PDF along with the link to the video so people can see the work as well.
I actually worked through most of the problems, and I have them written down.
Good, because I worked a couple of them too. I was hoping someone got the ones I didn't. We'll see how that goes.
The only problem is I'm going to have a little bit of issue figuring out which ones are which, because I did an absolutely fantastically horrible job at labeling them.
Legendary. All right, so that's that. So I can stop annotating. This is stupid. All right, let's fix that, shall we? Come on, clear. Oh, I can just do this.
No, I don't want to clear.
Yeah, I'm not a teacher, so I'm not good with the Zoom annotations yet. Here's his first problem. This problem is easy.
Yes.
So does anyone want to see how this problem is done, or would you like me to just quickly explain?
So this is like a super basic weighted summer. I would just say like the textbook does a pretty good job of explaining that. And to me, it's like you said, it's a pretty straightforward op amp overall. So I feel like
Yeah.
if you can do the basic layout, like you can do this one.
Yeah, I'll just
add in-
describe some important considerations. So this little node right here is the virtual ground. So we have 0 here. Using that, we have a couple other pieces of information. There's some current value I coming in, and that current value can be broken up into subcurrents for each of the voltage sources. That'll be important later. And then since this is 0, like this whole area, nothing comes in here because it's infinite resistance, right? The current from here, all this current directly flows this way over RF or whatever. So you'll have this should be the same current I. The way you solve this is you write an expression for this current based on voltages and resistances, and you set it equal to this current based on a, based on a total voltage, right? No, based on, what did I write it as? Based on V out and a resistance. And it lets you solve for V out with relation to the others. The final solution that I got was V out is equal to -10 V1 minus 5 V2 minus 4 V3.
I did this. I got the same thing. I just didn't distribute. So I actually have a negative value because it's a, inverting. So technically, if the equation for the voltage across the 100 ohm resistor for the current port would be VO minus VI over RF. And since RI, sorry, I'm going to say RVI minus VO over RF, that will become negative because, of course, the VN that goes in the amp, because RO is negative and it's ideal, will be 0. You set the equation of, all of the voltages and currents on the left side equals negative VO over RF.
Yep, basically.
Yeah, the way, like, I think this, and I mean, probably kind of all the problems, but definitely this one is like the biggest thing from this class to take, I think, is like the assumptions to know that like the voltage at that, what do you call it, the mother node is 0 and there's
know you have a
current going
virtual
in.
ground, know that nothing flows into the amplifier for some reason.
Yeah, and then everything else is basically just like Kirchhoff's law.
Yeah.
Mm-hmm.
So you do it once at the output and then once at, where those 3 separate voltages come together.
All right, yeah, so I gotta clear out of that. So that's that one. So I have that like worked relatively legibly on a piece of paper. So as I said afterwards, I'll submit like whatever problems I've worked along with the video for people to see more in-depth work.
Yeah,
so
and
this
the textbook also has like pretty much like a step-by-step solution for kind of going through like that exact problem where you just have the 3 inputs going into the 3 voltages into the 1 amplifier.
So this one, he actually just sent us a message about this one, and it says that this first stage is an integrator and this one's like a basic normal amp that just has a gain. Does anyone understand how to do this one yet, or shall we figure it out?
I actually directly emailed him probably a week and a half ago about this one. I can't remember. Let me see if it's on my computer. Which lecture it is. Essentially, he goes through an example with a resistor and capacitor op amp, where he basically solved for V out symbolically with any sort of thing. You have to use an integral, so it looks kind of funky. Okay, it's not going to be lecture 2. I'm looking at lecture 2. It's lecture, that's the wrong one. But the thing is, you set up the V out as the formula -1 over RC times integral of 0 t of Vn dt. So you have an integral.
Yeah, he said something about integral in his email. So what did you say the V out is?
So let me look at what you're looking at. Okay, just so the symbol. So V out for the capacitor one. Okay.
For this first stage.
For that one. So you could do V out in or whatever. Where it'd probably be better to do V in because it's technically V in to the right one.
No, I'll just say V out for
it
one.
doesn't really matter. But essentially that would equal negative, because it's inverting,
Yeah.
-1 over R times C, which would just be the raw.
Time constant. Well,
yeah,
RC is time
just the-
constant, but oh well.
Yeah,
Yeah.
you're just doing the raw numbers. You don't have to do anything funky with that, and that's multiplied by the integral of 0 to t.
Oh yeah, let's do it. There we go. Yes.
And then that's multiplied by, in this case, it'd be v1 dt. Or that's inside the interval. Sorry, not multiplied, but yeah, you're doing good. That's
so
right.
what, just v1
Yeah, v1 dt.
with respect to dt. So whatever function we were given for v1
Hmm.
would be integrated, then multiplied by -1 over RC. And this is the expression for v out for an integrating amplifier, or whatever
Yes.
this is supposed to do. And then we take this as the v in, whatever this results in, treat it as
Wait.
v1, and then work it normally on this side.
And with the other one, you can just use the basic formula that he gives us for inverting deals, which would, for the v out, which would v out of t would equal -RF. In this case, it'd be divided by the 50 ohm resistor multiplied by the input, which in this case would be the integral.
Multiplied by VO1. And 50 ohms is from here.
Yes.
Why do we leave out the 100 here?
That's RF. Sorry. I
Oh
don't know.
yeah, I forgot that that's RF. Yeah.
Yeah, when I have it written down here on my piece of paper, I labeled it differently than on here. I'm just making sure I don't translation error.
So the expression for V of t is the result of this, and this is there.
Exactly.
So you just chain them through.
And
then,
the
that actually clears out to be a very nice 0 gain. I'm sorry, 1 gain compound.
Do I hear unity gain? All right.
Yeah, exactly. So when you do all the math for that, it'll be v of t equals the integral 0 to t of v1 dt, which would just be, I think that would just be v1 of t. Because I think that's how the integrals work in this. I
That's
don't know.
about right. Well,
Yeah,
yeah,
and-
if it's with respect to t, then yeah.
And so also the expression for like the integral, that integral for the first integrating amplifier is on the cheat sheet too.
Oh,
It
okay.
is?
Yep.
Yeah, did I open that? I do. It's right here.
Oh, okay. I found it. It's on page 9 of lecture 5 as well. He has the integration via op amp is the title of it, and he goes through all of the long, funky, dunky, weird, stupid, long differential equation level bullcrap that I'm.
What happened?
Where is the? Here it is. Integrators right here. Yep, there it is.
Yeah.
And
So-
differentior. Yay.
I did. Oh boy, I did differential equations, and that was 1.5 years ago. I did it during high school. I don't remember any of it.
Yeah.
Yippee-ki-yay.
Taking it. I took it 7 years ago.
Oh
Jeez.
Lord.
How do you even
Yeah.
manage that?
Huh? Well, okay. So I'm actually back at UAH to get my master's degree.
Mm.
Ooh,
I have a bachelor's
big man
in
in the
computer
house.
engineering already.
Electrical. Dude, he's better than us too.
I would not say that. I would not say that.
He's just been around. He's been
Yeah.
around. He's put in his time.
All right, I'm gonna clear this annotation. So that's
So,
the
do you
solution set
think-
for this one.
So, do you think like for this, do we need to derive the entire like expression for the first, like the integrating amplifier, or could we just take it from the cheat sheet?
He
and
gave
then
us a cheat
derive
sheet.
the
You
rest?
can take it from a cheat sheet.
That's what I'm thinking.
Basically, you just set up. Yes. You label the whole where V2. I've labeled as V2, which is the V out for the first amp.
Uh-huh.
And you just label that as in that equals negative, and then plug in the equation, and bada bing, bada boom.
Yeah, in general, even if I weren't given an equation sheet, I would never derive equations unless expressly asked to. If it was something like this, I always would be like, I'd write like integrating amplifier, therefore V out is, and then I'd write
Yeah.
the equation.
It's like you don't have to find the proof for the Pythagorean theorem.
All right, we have this one. So I was actually talking with Hayden about this one earlier. right the Zoom call started. So this is actually discussed in the cheat sheet. I just saw it when I peeked at it again. So we have a couple different things. We have RMS value is figured out two different ways. If you have a sinusoid, which we do, it looks like, you get to do what I actually, yeah, you get to do this. Multiply it by √2. If it's just a function and it's not nice, you got to do this. But in this case, since I'm pretty sure these are counted as sinusoidal values, we just get to say, hey, what's the max value of VT or IT when sine is equal to 1? What does that value work out to be? 10 and 40. What does that mean? It means V of t expressed in RMS is going to be 10 times √2, which is going to be what, 7.07?
Yeah.
And then over here, current expressed in RMS is going to be 40 times √2, which is going to be a number. Definitely something on some number. I'm not that fast.
Yeah, and if we're going based off like where he said, like everything's based off like the homework and examples in the textbook never uses that first formula. I mean,
Yeah,
it's on
this-
the cheat sheet.
This would
but-
only happen if he gave us, it would have to be something that's a signal that isn't sine or cosine, because if it's a cosine, then I just convert it to sine anyways and do the easy way.
Mhm.
And
So it's
so
like B of
essentially
t,
is
like
just-
that's, x squared or, something like that.
Yeah, if you were to
Yes.
give us something weird, then he'd just
Yeah.
do it that way.
Like I guess a square wave or something of that nature.
Ouchie. All right. Then that's 4. So far, honestly, these tests don't seem too sus. I'm sorry I said that. These tests don't seem that bad.
Well, that's assuming that this is how the actual test is going to be.
Supposedly, this is a test he's given in the past.
But
2017.
it compared to the homework,
I honestly believe, given the homework that we have to do, the amount of homework and all that stuff, honestly, I believe that this is the kind of teacher who batters you with assignments and hypes it up to make it seem like, oh, like the test can be this hard, you need to master all the homework examples, but it's actually a trick because he doesn't want you to actually perform poorly by slamming you with hard things on an exam when you're under time pressure. So he'll give you, a very acceptable exam. And then,
And he
and
doesn't-
also he said that there are going to be test grade adjustments.
I think he said that there'll be adjustments if needed.
Yeah. Well,
Which
he
at
said,
this level, once you get past like sophomore year and you're into like your last 2 years of college, it tends to become more common, or
oh,
not.
yeah.
Really depends.
I don't know what it'll be like this year, but I've heard from people who have taken him prior that he's very particular on like his partial credit and things like that. That if you like write something wrong or if it doesn't look like the correct letter, then he could count you off or stuff like that. So he could be easy, like what you're saying might be true.
We shall see.
Maybe he's going to be generous due to the circumstances of the course being online. But then I've heard in the past where people say he's a very nice teacher, gives partial credit, but then he's very maybe stubborn in his grading too.
Yeah. Well, luckily, what do we have? Does anyone remember how many exams we have? Is it 2, 3, 4?
we have
Two.
3 including the final.
Yeah.
3 including the final. So 2 normal exams that are like a replacement of midterm essentially, and then 1 final.
Mhm.
Okay. So, well, as long as everyone gets like a 70 or 80 on the first exam, everyone should be sitting pretty.
Yeah. Also, like speaking of the exam, like is he going to be using Lockdown browser?
I have no clue.
All right,
What?
he sent out a
Because
thing.
like
What
I'll
he's going to
just-
have us do is he's actually going to have us download it
The PDF.
off. I get a PDF, so you could print it or whatever.
right. So what I'm assuming, like my plan is I'm gonna whenever I take the exam, I'm gonna print it off, and then I guess I'll be timed on Canvas during that
Yeah.
whole time, and
Yeah.
then I'll.
I
work
think he
the
said he
problem.
factored in like 10 minutes of time, which you could use for the printing and scanning.
Yeah, but then you're not submitting it on Canvas, so the Canvas assignment's never gonna close. He said to email it to him, so
That's a little weird, but
yeah, like
There's a lot
I don't know,
of
dude.
stuff. I'm just, it's weird.
yeah. Well,
I'm concerned
he-
if he
he-
uses Lockdown
Campus is
browser.
open. Campus is open on Tuesday. Let's be real. He doesn't use Zoom. I'm like 90% sure he couldn't pull off Lockdown browser.
Yeah, I was gonna say if he tries to do it
Lockdown browser is annoying too, like for teachers
Yeah.
and students. So it's a hard thing to use in general.
Yeah.
I've had 2 math classes where they just would prefer you to get on a Zoom call with a
Oh, yeah.
phone.
Yeah, same.
Which I honestly prefer that.
Zoom proctoring is the superior method.
I concur.
But either way, so we have in-person class allegedly on Tuesday. So I'll go in and batter him with questions to get all that stuff squared up so we know what's
Yeah.
happening.
I'd almost like, if he hasn't said anything about it, I'd almost rather not mention it because I don't want him to try and figure it out in like the last day and then it be a disaster.
Yeah, we'll see.
Hey, maybe he'll make it an open book test.
Yeah, there you go. I mean, given the cheat sheet and everything thus far,
It basically is
like,
open book.
I feel
Like,
like
you
you
put
I
a
feel like
lot
you
of stuff.
almost might be hurt if it were open book because you're like spend more time flipping through the textbook trying to find stuff.
Yeah, open book is in most cases almost always a hindrance
Hmm.
because people will feel overconfident. They won't do any review and then they'll get crapped on because their notes aren't good enough for them to be overconfident.
Yep.
Either way, number
This one I
5.
think I worked out. It makes sense. It's based on an example he had though.
Yeah, I think there's a couple in the homework that are basically worked identically to this one.
Yeah, and yeah, the textbook has multiple examples. Like this is pretty much just like a straight up
Yeah.
voltage gain amplifier.
Yeah.
I
So
think this exact one is one of those 4 defined in the table in chapter 1.
all right, so let's just write down the final answer equations for this. I have a couple. So we have AV. It says AV is equal to VO. It's just find equations though. So obviously we don't have any values. So it's going to be equations of composite resistance values and voltages. So let's see. Down here, it is going to be, so we need to find V out. So V out is going to be over here. Obviously it's going to be across RL. So the, what is it? So AV, oh, that's big. Let's lower that DPI and clear that.
Yeah, so I think it'll just be like basically for V out is just voltage division to find V out. So I think it's like RL over RO plus RL times AVO VI
What for V out itself?
for V out itself.
All right, we'll do that one first then. So we have V out. And what did you say?
So it's pretty much just like seems like straight up like voltage division across like RL, like you said. So V out equals RL over sum of RO and then you multiply times that AVO VI.
Or just 100 and VI if you want.
Yeah, 100 VI. Yep. And then all you have to do is do it again on that first loop where the voltage source is. And then you just plug that answer you get for VI into the equation for VO. And that's your whole, and then you just divide both sides by VS. And that's your expression for your voltage gain.
I
Yeah,
actually
so-
did it very similar to you, but I found the yes, and then I just put them together, VO and VS, and then the VIs cancel out when you do that.
Mm-hmm.
You know, there's always more than one way to skin a cat, though.
Yeah.
And this one's just, is it just
Same.
this or is there?
Times VS.
Yeah, just VS.
And then when you plug that into the first equation, that'll allow you to get V out over VS, which is AV.
Yep. So AV is going to be some composite resistance. Cool. So anyone who likes to do algebra, I'll leave this as an exercise to the watcher. You can do this part. So I'm going to clear that. Yeah. So this is the last part.
Well, I think that we still have to find for number 5, you have to find the formula for
Yeah. Oof.
I
Current-
over
current, yeah,
IS.
current.
It's a lot easier to do, though.
All right, so for current, let's look at this. So we're gonna need voltages divided by resistances here. So for our IN or IS, I guess, it's gonna be, what is it? It's gonna be VS divided by the composite resistance. summed. So VS divided by RS plus RI is equal to IN, and then IN goes over here. And then for I out, it's gonna be, what is it? Is it load or is it RO that gets in the numerator? It is neither. Okay, it's simply gonna be what, AVOVI over AVOVI, right? Or is it just the number? I think it's just 100 times IN over RO plus RL. Let me see, like this. So over here, if we have IN, oh boy, let's do it this way. IN is simply going to be VS divided by RS plus RL. Come on, RL. Then we have I out, which is going to be equal to I out, which is going to be equal to, is it this whole portion or is it just the A?
The whole portion, because that's just a multiplier.
Yeah, that's what I thought. So we're gonna have A, V, or whatever, VI over RO plus RL here.
Yeah, and with the
With the
first
current
current, is
IN.
that supposed to be IS?
IN, IS, whatever, yeah. Let's change it to S.
I guess it works. It's just
Yeah.
that on the formula they have it
Yeah, it's IS. So change to RS, then we have RO plus RL here. And then yet again, IS, take this, put it in here, solve for IO over IS, because AI is equal to IO over IS. And you're done. There we go.
So where in that second term, where do you get the multiplied by RS or IS, excuse me?
It's what I did in another example. Let's see why, just to make sure. Well, first off, the reason why is because unless we have IS in the term, it's
You
not
don't get
gonna,
the gain.
yeah,
Right.
it won't be able to get the gain, so it has to appear somewhere. Now, why is it multiplied? Let's look back. It's because the IS is coming in, and it's being acted upon by this multiplier. So what is it? So it's a current times a voltage, VI or
What
whatever.
I did is I just did a good old KVL equation.
Demon.
Whereas AVO times VI minus IO, and then in parentheses, RO plus RL.
Mm.
And then from that, I just got, because of how, wait, hold on, did I swear, did I just do some, I just lost something, hold on.
Well, could IO not just be well, maybe that wouldn't work. Would it just be like the V out over, no, that wouldn't work, I don't think. V out over the sum of RO, RL.
All right, yeah,
I'm not sure if I don't think so, because I think there is current gain here. Because otherwise, then if it were simply just like the sum, if it were just V, you said V out?
Well, because is I constant throughout this second loop? Like the current
yeah,
constant?
it should be constant through both loops.
Yeah.
So
Because
what did you say it should be instead?
Well, I'm just wondering, like, if you did like mesh analysis on that second loop, what would you get on the right hand loop?
Over here.
Or
just do a KVL.
node? Yeah.
And then you just get AV, the AVO, and then the VI, and then that's over RO plus RL, and then you're all sorted.
Yeah, because that gives you, because current is voltage divided by resistance. And then you plug in Then how do you get your term for IS?
I think these are
IS VS over RS plus RI.
VS over RS plus R. Well, we have that right here. So you're
Yeah.
saying that it doesn't have to be composite. We just solve for these separately and divide
Yeah, you
them.
can just solve them separately and put them in because that's all you're doing. If you have IO, you know what IO is, and
Yep.
you know what an IS is. You just need to find the equation. If it's the equation works, then
Yeah.
it works. And then you just plug them in and
Now that I'm thinking about it, I'm pretty sure that these are the same thing. Functionally, they do the same thing. If you do it this way, where you multiply this onto the numerator, it's functionally the same as just dividing them.
Yeah. you're just doing a weird flip thing.
Yeah, adding a step. But yeah, so you solve for this doing some loopies here, and this one, in my opinion, is a little easier because it's not as confusing with this part. But
Yeah.
this just
Well,
sits in the numerator
If
anyways.
you swap out the AOV for 100 when you start up doing it, as long as you remember that the only number your entire thing is that, it makes it a little bit less confusing.
Fair point.
Because you just think, oh, it's just a multiplier. Yeah.
All right, there's that then. So that's how that's done for both AV and AI. This is the one that I had troubles with.
I found an Indian guy that did a great video on this.
Legend. Yeah, the reason I probably had troubles on this is probably simply because my Theven and Norton isn't perfect yet.
I forgot how to do it earlier today.
That's what happens sometimes.
Yeah, I re-educated myself.
Is this just like straight up Thevenin like equivalent circuit analysis?
Your
Um,
task, what is the Thevenin voltage, what is the Norton current, and what is the
Yeah.
internal resistance?
Yeah.
So we're given some data. We have no clue what's in this black box, supposedly. We have to figure it out. So this is reverse engineering. So let's go down and see what we have available to us data-wise. So we have an unknown signal source that produces a voltage across some load resistor. So the load value that we've been given here is right here. It's 100 kilo ohms. Cool. And we have produces a voltage across, and then we have a potential across this. And then come on, arrow, and then we have 40 volts. Never mind. It's supposed to be 10 millivolts across the load resistor.
There's two different things. So
Two-
essentially,
yeah.
you're going to have two different loads you're going to plug into it. It's going to turn into a system of equations. is what I'm
Oh
saying.
yeah, I see it. So this is correct for case 1. Data point 1. Data point 2 gives us a 10K resistor for the load and 10 millivolts across it. Your task, from the experimental data above, what is the Thevenin voltage, the Norton current, and the internal resistance of the signal source? So
basically, all we're doing now is just assuming, okay, for the first one, whatever's in the black box, we're going to assume it's a Thevenin equivalent and then do our analysis on that based on one or both of the data points we're given.
I found a Slater worked out version of this from some guy that sounds Croatian, so I trust him pretty good.
Croatians,
So-
they know what's up.
They do. So the way he did it, and I followed through and it worked. It was different numbers, but it's same process. Is you just draw your good old like Thevenin, like they already drew it for you essentially. But the Thevenin voltage, you just set up where it is. You're doing a voltage division equation. Okay, so the voltage that you have across the load. So for the first example is 40 millivolts. You
Yep.
have that equal to the unknown voltage of the Thevenin multiplied by the R hold on. Yeah, the R load divided by R Thevenin plus the R load.
So what did you say? It's this
Yes.
is equal to
times V Thevenin or V source, whatever.
So
however-
this times VS?
that equals
Yes.
VS. And then that's going to be multiplied by parentheses. R load, you could do, I did it R load and divided by R load 1 plus RS or R Thevenin, however you want to do it.
We'll just do S because it's faster.
Okay. And
So
then
this is for the first one.
and then you do the same thing for the second one. And you could fill in RL if you wanted to, but we can do that later. And then after you do that, you're going to be doing simultaneous equations. And you're going to solve, the way I did is I solved for the RS first.
Solve for RS and sub back in, solve for VS, and then you basically do this same equation with a Norton equivalent and do current division instead and solve for the remaining unknown, which is
Yeah, so we
IS.
have this value, we have this value, we have this value, we have this value.
So you have two equations, two unknowns.
Mhm.
And with what you're saying with how we solve it, the best is that and I forgot about this until the I Norton, if you know the V Thevenin and the R Thevenin,
Oh,
you just
do
do the
Ohm's
good old
law.
Ohm's law. Yep.
Yeah, that's right.
So
It
where
gets
do we, so our source is our R Thevenin, right? And or the internal resistance.
R Thevenin is is the source.
Mhm.
So we solve for both the Thevenin voltage, the source, and then as you said, Ohm's law yields us the Norton current.
Exactly.
Yes. So in this situation, or I think you could also solve it starting from the Norton equivalent circuit, do current division in the same way. Solve for
yes.
Thevenin.
That's for
solve
cringe people.
Yeah.
You
Solve
see,
for,
I'll do it the Thevenin way because they already doodled it for me.
yeah. Oh yeah.
I
It's
think in voltage a little bit better than current when it comes to equivalence.
same, but I'm just like, that's an alternate.
If you were
like,
so
way to get
inclined.
to the
Hey, it
problem.
gets the job done.
Yeah, there you go.
It does, I
Hey, if
suppose.
it gets me full credit on the test, I'm not gonna knock it.
Yeah.
I don't
Alright.
blame you. But that's always a good thing to remember. If you just completely brain fart how to do it one way, then you can do it hopefully another way.
Mm-hmm.
So this one, so this one's not as difficult. So now comes to the part where we start theorizing whether or not this is actually representative of what we'll be doing on Thursday. Also, actually, a more important thing before that. So anyone who's like here right now, is there any questions or topics we'd like to clear up? Like for anything, like I could click onto these and like scroll through these real quick.
I mean, his notes are not the easiest thing to read through.
Yeah.
I guess like I can't think of anything like specific because I feel like most of the circuits you'd have to do are like amplifier circuits. I don't know, hopefully would be straightforward, but yeah, he could give us like one of the more difficult ones.
Oh, here's actually, let's look at this real quick. This is pretty useful information. This PowerPoint right here is lecture 4 op amps PowerPoint that he has. I recommend everyone goes through and just memorizes it. It's basically all the vocab that we could ever want. And look, literally right here is where that answer was.
Oh
For-
my goodness.
So this PowerPoint right here is like definitely the key to the true and false straight up for this entire like chapter. If you have this memorized and then just surface knowledge of everything else, guarantee yourself 10 points. Easy peasy. Yeah, so we have differential input signal, how to calculate that, how to calculate common mode signals. So we haven't been asked explicitly how to do these, but it's definitely good to understand what this is asking.
Yeah.
And then common mode signal, we can write these in these and then a common mode signal is one that is common to both lines, which makes sense. Why is noise common to both lines? Because noise sucks.
Oh
That's
yeah,
why.
and if you wanted to give like a 5-point problem or something for this, because like mathematically these are really easy, but these equations are not on the cheat sheet.
Ooh,
So
sneaky.
yeah, Exactly.
Yeah, cover these things. If you ask for differential input signal, if you ask for common mode signal, you can calculate them based on, yeah, see, because this is actually something I had no clue about, because this wasn't in the homework, I don't think. Like calculating these specific values. Like if we went to the test and were asked calculate the differential input signal, I'd have a panic attack, but look at how easy it is. It's literally just, I mean, this one's kind of easy to figure out. It's just the difference between V1, V2 of your inverting, non-inverting. Common mode is obviously a little sketchier. It's 1/2 of that.
So
But-
I will say I mean, I guess you can do it either way, but the book defines the common mode as 1/2 V1 plus V2, which to me, I'm just like, oh, you just take the average of the two.
Yeah, whatever works, I suppose.
Yeah. But yeah, all you need to do is know those first two equations, and then you can use both of them to find the ones in like bullet point 3.
I love that he just wrote, this is a big deal. I actually, now that I think about it, I think I understand why he wrote this as a big deal, because I'm pretty sure by the definition of like the differential amplifier and everything, like if something's common to both lines, it gets negated to 0, right?
Right. Yeah, that's why ideal op amp has to have common mode rejection.
So
because
that
then you're
doesn't
not- you're not-
happen.
Right, because if you have the same input and out, or the same two inputs, you're amplifying nothing.
And then you create a black hole and the universe collapses in on itself.
Yeah, not ideal.
All right, let's just skim through this thing since it seems pretty useful. Let's just go back to the top real quick.
And then one thing that
useless.
everyone does need to memorize are the 4 types of op
Amp.
amps.
Yeah,
amps
I
and op
think
amps.
that's not in this one.
Yeah,
Yeah, this
it-
is him explaining how to.
Yeah, no,
as-
I just wanted to put that out there. We're good with staying there. I just wanted to regurgitate that out before I
Yeah, I'm
forget.
just gonna check if I have that lecture open already for varieties.
Yeah, because what is it? The voltage, amplifier, current,
Conduct-
Oh, you just passed it. You just passed it. Yeah, hold on. Yeah, one more, I think. One more. There we are.
Here we
Cool.
are. All right, I'm gonna zoom up on this. All right, so here we are, everyone. Remember all the ideal characteristics and gain parameters. Let's get it. All right, voltage amplifier, the most standard and plebeian level amplifier. No one likes them, they suck. All right, current amplifier, slightly better than the voltage amplifier because it hurts you more, but it's still kind of annoying. Transconductance, funny name, big pog. Transresistance, eh.
What if you wrote funny name Big Pog as just like the definition? I think it might like blow his like he wouldn't be able to comprehend it to the point of like that just be it.
Funny name, Big Bob. All right, but legitimately, let's go through these. So he explained the transconductance and transresistance amplifiers, but does anyone remember specifically what these
It's-
actually even?
Yes,
written
yes,
right
I did.
below.
I did actually.
Alright.
I watched it literally today. Let me remember it though. Okay, it's really. He said that it's a very niche thing, but
Yes.
essentially, all it means is you have it's like they're basically amplifying resistance and
So
amplifying conductance,
yeah, whatever that is.
which the
It's
inverse
just,
of
yeah, inverse
it's
resistance.
the inverse of resistance, which is like which and so basically it's one of those things that like you use like 8 of them in like for super high-end stuff. Like it's just one of those really niche things, but something that for whatever reasons in text.
Okay, so what I'm hearing is that, and now when you look at it, it's pretty basic. When you look at the gain parameters, open
Yeah.
circuit and voltage gain and and short circuit current gain is given as parameter A with subscript I, S, or VO. So that tells you it's voltage, it's denoted voltage, and then transconductance is amps per volt, and then resistance is volts per amp. So
So-
the difference between them is their ratios are current and voltage dependent as opposed to voltage or current dependent.
And also one in their ideal parameters, the opposite.
Yeah, transconductance is all infinities and transresistance is all zeros.
it looks like a probability problem, and like let's see all the combination of
Yeah.
ideal parameters. And then
Real
make-
quick, does anybody else remember when we started talking about diodes and stuff, and he mentioned the diode with negative resistance, and I had a heart attack? Like
So
I don't remember that part.
for about it was called a tunnel diode, and there's like other ones. So I literally spent like a week after I heard that doing nothing but researching what these things are, and I hate them. They suck. So all they do, like when I say negative resistance, what does that mean?
That does that mean the does the
is
current
that
get
conductance?
No, it's not. That's the best. It's not. It's no. If you have negative resistance, then you have negative conductance. Like, what does that mean? So I looked into it, and here's what it is mathematically. It's called differential resistance or something.
Oh,
And
no.
what it does is if you increase the voltage across the component with a fixed resistance value, the current drops across it, which sounds
Oh.
like bullshit, but it exists. And a great example of it is supposedly, what is it? Fluorescent light, like the fluorescent lamp tubes or whatever, like the light tubes.
Mhm.
Yeah, the ones that you can hear.
Yeah, those things. Yeah, so they suck. So that's interesting.
There you go.
Hence
So is
the
it like
reason-
basically for these? Because I feel like where they're gonna show up is probably like in one of those true or false questions where he's asking what it
Yeah.
does.
Although at the end of the day, if you were to have us analyze it, it's not
Oh,
all too impossible. You just calculate your V out and your I in, or
yeah.
your
I
I
mean,
out and V
The
in.
main thing with these is if they give you this equation. So if they do the transient amplifier and they have and you have this equation now. For example, it's a RM, I think is what that is, equals VO divided by I, II.
Mhm.
You could use that equation for the open circuit hit trans resistance if you to find the gain, of course, but also you can find other stuff with it.
yeah. So if you're given RMII, you can find V.
Yeah, your V out and there and so forth and stuff.
Exactly, with like no steps.
Easy
Mhm.
peasy. All right, so that's how we do
Yeah.
that. So let's go back to this thing.
What does he say in his notes, real quick? I thought I saw like definitions for those.
Yeah, there they are right there.
I mean, yeah, this is what he said a couple seconds ago.
Okay, gotcha.
It's a booster or reducer. I didn't know. I forgot about the reducing part.
That we just have-
Ugh.
that's all that is. So let's go back to this one since this is probably covering all the true false topics. Everyone understand this?
Triangle.
Yes. All right. This is so this is what I said earlier, how we never actually draw this part.
Yeah.
But functionally all op amps have to have power rails.
Hmm.
Oh, that's what the power rails are. Okay, I'll
Yeah.
write that.
Yeah, that'd be a good. That'd probably. Well, it was a true or false question. So
Yeah, straight up was, yeah. So this
Yeah.
one might show up. It's good to remember that power rails are a thing, rarely if ever, because when it comes to our analysis of the op amp, since we're operating almost exclusively in the ideal range-ish, not really, since we actually have resistance values sometimes, but since we're just considering, they're like, oh, well, there is no upper limit to the current gain. Oh, there is no upper limit to the voltage gain. Therefore, theoretically, we just have infinite rail power.
Right.
But that's not how it works. So when it
Yeah,
comes
I
to real
think-
life, we got to consider that.
Yeah, I think probably like for the sake of like the problems that we've been working, or you might see on the exam, you just are assuming that whatever voltage you're working in is within those rail constraints.
Yeah, and whatever gain you get is not gonna break the bank.
Exceed, yeah.
Then we have
then- And then where those come in is just like a power balance on the
yeah.
op amp.
Then we have this, which is just a rehash of all the ideal things, between terminals 1 and 2, infinite internal resistance. So that's why we get to say the whole, hey, guess what, virtual ground node, which I'm 90% sure appears later in this slideshow or whatever. Then we have dependent source is based on the difference between V1, V2. That's where the whole gain stuff comes out. Then it just defines our terminals. So terminal 1, aka the negative terminal, is called the inverting. Terminal 2 is non-inverting. Cool. Yeah, and then part 5, he straight up talks about the virtual ground. Cool. This is the ideal. We've gone over
Oh.
these a bunch of times, but we'll list them one last time. Characteristics of the best op amp: infinite input resistance or impedance, whatever you want to say, 0 output impedance, 0 common mode gain, or equivalently infinite common mode rejection, infinite open loop gain A, and infinite bandwidth. You want it to work everywhere. You want it to give you infinite energy. You want it to never have to subtract and make a 0. You want it to have no output resistance, and you want it to have no input resistance.
Unlimited power.
Yeah, ideally, of course, I would love some of that. Then we have the thing where it talks about the common mode. So this is a slide that gives us the definition of common mode, which showed up as a multi or a true false question. So it's good to know these or understand this now. Common mode just means it's on both lines. That's the definition of it, and noise counts. This is the one, we don't have to know this.
I feel like though that one, so in the textbook, like they have you like derive an equation representing V3, and it's not that difficult. So I could see him putting something like this on there.
Yeah.
Since it's in the slides and it's in the textbook.
Yeah, but this slide looks like he's talking about common mode and says that we keep it simple. So I have a feeling that he's not
yeah,
going
that's true.
to throw this on us.
We're not going to the fourth dimension of math.
Yeah, that's no good. All right, so we have more definitions. We have open loop, which implies no feedback. So this is not an open loop. This is a closed loop because of the feedback resistor. The feedback resistor is headed to the inverting output. Therefore, this is negative feedback. Cool.
And so that's what from the true or false like basically helps drive the game.
Yes,
for
that's
the output.
what keeps you from that infinite part, because as our glorious instructor said, an infinite gain op amp is a horse with no saddle.
Yeah, so the feedback loop is the bridle and saddle for the
Yeah, this
the
lets you make the horse go where you want to go. What is this? This is him talking about the virtual node rules because of the open loop, so nothing goes in here technically. So we can just say all the current flows here. Yay. That's that. Observations needed. Oh yeah, okay, so it is true. So here, look, this is 0. What does that mean? That means nothing's going in here. That means this current has one way to go and it's here. So I1 is equal to I2. He says that next. Right here. I1 is equal to that. I2 is equal to that. And then he just says think KVL. So cool.
Yeah, so it's like KVL between the
Like this part and this part.
V1 and V out. Yep.
And then we have this last slide here. Closed loop inverting op amp. I think, yeah, we just looked at this. And I think by this point, everyone's got this part down.
Yeah, that's like your textbook, like classic closed loop.
Yeah, if we get this on the exam, I'll be happy.
Yeah, and it's just inverting because your output voltage is going to be negative.
Yeah, John's shooting to the inverting output.
Mm-hmm.
So I take it if this were headed here, it wouldn't be inverting.
It would be
No,
VO.
that would mean it's positive feedback. I think if it's a non-inverting, then the power and the ground switch spaces.
Yeah,
I think
so
what it would. Yeah, go ahead.
I was going to say, so the textbook talks about like positive feedback. If they were connected between terminals 3 and 2, you would have positive feedback. But this says it generally causes the op amp output to saturate rather than providing a stable gain, which is why you use the negative instead of the
So positive feedback sucks.
Basically, that's what I'm getting from the textbook.
Understandable. All right, so that's that. Let's look through here. It's talking about bandwidth and stuff. Nothing more here. This is 3 real quick, so I'll just scroll through here, see if anything pops out. I think a lot of this is a lot of theory stuff. Oh, he's talking about this stuff.
Mm-hmm.
So convert this to decibels. So that's the decibel conversion for voltage and current. And then he also shows the power. Cool.
Yeah, and the power is only multiplied by 10 because the V term is squared, right? For power, like, yeah, V squared over R rather than it just being linear.
Yeah.
Yeah, if you calculate it this way, yeah. Actually, I think you have to calculate it this way.
Well, you
Well-
can just put the current in.
Yeah, the way I've been
Multiply
doing
it.
it is I just do it this way where this has already been calculated.
Mhm.
Wait a second.
I
Well,
typ-
you can do the voltage times the current gain.
Yeah, you can
Yeah.
do that, right?
I was gonna say I typically have found like because it's usually asking you to find all three of the
Yeah.
gains, and so I typically find voltage, current gain, and then just multiply those two.
Yeah,
with
you
the
can do that.
power.
That's how I've been doing it this whole time.
Yeah.
That's allowed, right?
Yeah,
Yeah.
yeah, because like voltage times amperage is power. P
Yeah.
equals IV.
Yeah, we'll go with that.
That's the whole thing of when we had it back in certain normal circuits. We had it.
What the hell?
He
Yeah,
like
I know.
blazed through that in like probably 10 seconds.
I mean, I'm pretty sure this is just deriving how this thing works, and then we're never gonna do that because he just gives us this part.
Yeah.
It's a
If he-
beautiful thing that a really smart person does that we just have to deal with now.
Imagine deriving stuff. I'm not a math major. All right.
Yeah, if he gave us that, that'd be a waste of everybody's time.
This is not the right thing. This, yeah, he gives us the part, so easy
Mhm.
peasy. What is this? This is more discussion of, and this is what I'm saying. Oh, for sinusoid, you can just do easy peasy.
Yeah, I think all we really need to know is that it's like what multiplied by square root of 2.
Yeah, which is also on his sheet anyway.
Mm-hmm.
And so with that, if you have the sinusoid, so if it's 10 times sine whatever, then to find the peak, you just divide. Wait, the peak is that number, right? That's in
The
front.
peak is that number
Yeah.
because like
Okay. In the
the
RMS
first-
value, you just multiply that number by the square root of 2 and you're good.
yeah, because I
Yeah.
think like one of the first
Hey,
equations in the
weighted
book
summer.
is defining like the base equation for like V out as a function of like V in over time or whatever.
It
Mhm.
looks like he has examples for the non-inverting, but I don't think in all of the homework I've never seen a single one of these.
Wait, which one?
It's the
Non-inverting.
non-inverting. So if it'd be a non-inverting positive if the RF feedback was plugged into the same line as the voltage
Yeah.
source.
It looks
or-
like he does full derivations for everything in this, so if you really want to know for sure, it's used for the viewers at home.
And that one probably like if you want to look at the derivation, that probably lines up exactly with the problem from the exam.
Oh, that VO equals VI, that right there, that equation is fantastic. Right
This,
there. Yeah,
is this for everything or just
that's
this?
for the gain.
Like this is a general case for gain across the board or just for this?
For that, that's for non-inverting. So for inverting, it's the same thing, except it's negative.
Isn't it, don't you like flip the resistances?
So I think the
Isn't
gain,
isn't for an inverting, the resistance sum is on the denominator?
It's a
for
little
it-
bit different. So like scroll, let me
Yeah.
see what his R2s and R1 is. All right, so R2 is the RF and R1 is, yeah.
Let's call it
so-
our, well, in this case, it's just our ground or something. I
Well,
don't
and
know.
I guess he's got so the signal source is going to the second terminal. So
Yeah.
rather than the mother node or node X being 0, it's equal to VI, right?
Brain go burr.
I think so.
It does say Rn equals infinity in this. So that, okay, never mind. That was worthless to say.
Well, this one is A is equal to infinity,
Yeah, yeah.
which means VO drops to 0, and we just have a VI expression of VO on the other side. Yeah, so this is a little wacky. So
the-
here's at node X. At node X, the expression. What is this even?
That's just a hypothetical. I
Okay.
read that too, and I'm like, that's basically, I'm trying to remember what exactly that's technically supposed to be.
Yeah, so it's just the voltage at that node X point is equal to R1 IF.
All right, that makes more sense.
And then he's just expanding what
Yeah.
IF is where it's.
And in this case, actually, yeah, okay, I'm starting to see this. So voltage, our source is down here, and this is a ground sink. So our negative feedback, because yet again, look, it says this is still a virtual ground node. Nothing comes into this terminal. That's why it's a ground node, virtual ground node over. So you come over here, and the IF that comes out from the V out just goes right over R1 through node X and goes to ground. So these are the same. So you solve for this side, and you're done. Because then you'll have a way to represent relate the relationship between R1, R2 IF with V out. And VI somewhere else, somewhere, I'm sure, probably.
Yeah, so then VI, oh, and then he's just using like the basic
VI
equation for-
minus whatever this is, VX, I guess, times A is equal to V out.
right.
That's the general
And then-
understanding.
And then right below that, he summed in, yeah, the expression for VX.
And this A drops this whole thing to 0, which allows
Yep.
you to just flip them and they're done.
Yeah, so there's really nothing like application-wise that's new
Yeah.
for this non-inverting. It's just different, like sources and ground are in a different place.
Is this more of the?
Yes.
Yeah, we're just gonna assume it doesn't show up. For real though, I'd recommend everyone go through and like look this over.
What was that you just like? What was that?
All
for?
of this.
Well, scroll up a little bit. I want to see what the top
What
is.
is he deriving the
All right,
equation?
let's
call-
recall this equation.
Okay.
So he just freaking sends it.
He wants to say this isn't infinite, and now he wants to derive
Oh, so he's like,
A or something.
okay.
So this is where it stops. A is, infinitely larger than 1 plus R2 over R1 for small areas in non-inverting op amp. Well, non-inverting op amps suck, so I refuse to acknowledge them.
What you mean? You don't enjoy all that?
I absolutely hate non-inverting because they're stupid.
Okay, there's the voltage follower. Which
Oh no, it's a non-invert. Either way, the voltage follower, 100% negative feedback, lit. It's actually pretty good. We had a question about the voltage follower.
That's the one that
Here's
has
the-
the unity
There's
gain.
the
Inverting configuration. Let's look through. What? No. We're gonna go back to the voltage follower. Voltage follower simply has VO equal to VI, I suppose, because it is a unity gain amplifier. Vocab word's fun. Therefore, VO will be equal to VI. So that's the first major piece of information we have. Hey, look, he says gain's equal to 1. Cool. Claim to, there's nothing here. He just talks about it.
I think he's just proving
It's a
that
transducer or something.
like just knowing that VI equals V out, and it's like basically a buffer amplifier.
That's why it's really hard to like follow along on a video with him, because I'll like drift off into Never Ever Land because he's talking about random mumbo jumbo that's fantastic to know about, but I just can't. And then the second my brain goes off to Never Ever Land, he explains something super important.
It do be like that.
Yeah,
do
all right.
like that.
I've like more or less stopped taking notes when I'm
Yeah,
in
I don't
class.
take notes in his class at this point, just
Yeah.
because they're all going to be posted. I just sit in there and I just kind of watch what he's saying.
Yeah,
just-
helping like taking notes helps me, but like I only do it when I'm watching the video because I can pause it. Because
Right.
like
I mean,
just
right,
is
I'll
gonna
go
blur
back. It's
through
just-
whatever I'm looking at. Okay, so he calls out specifically from like one of the last homework assignments from chapter 2, knowing something about the D'Arsenval meter movement and how we're supposed to assume that. And that was one of those that I totally just glazed over
In this
on.
thing, he talks about it somewhere. This.
Yeah.
So I actually emailed him before the semester started because I looked him up and I wanted to see, and they said, oh, he's not super technologically, inclined. and I emailed him and found his UAH number, and he's like, I'm non-informed. I'm going to be teaching that class this semester. So he didn't know until probably a month before the semester started, if that he's teaching this class.
Jeez.
I mean,
Well, you see, here's the
Come on.
biggest problem. The biggest problem about this slide right here is it says the word torque. So that's done.
I feel like within a month you could get a lot done because some teachers aren't told. I had my physics 3 teacher, she didn't find out she was doing the class until 3 days before.
Oh my gosh.
Now, first day was rough, but after that it went smooth sailing. But she was also like 24, 25,
Yeah.
so.
All right, so
Then you also think though he's been teaching this class for years, over and
Mhm.
over again.
Yeah.
Yeah, I mean, he's literally like, if you go back to that lecture 6, he's just crossed out like 2020 and put 2021 at the top of it. So
we'll just go through this real quick and make sure we've covered the general points, I guess. And
Yeah,
read
fall
through these.
2019. Yeah, it's going to be fine.
Hey, are you going to post a link to the group me of the recording of this? Because I've got to duck out.
I will, yeah.
All right, thanks.
No problem. All right, so let's look at this. Let's go through and make sure we understand everything. I'll just read through the know and understand portion. Voltage gain, current gain, power gain. What do we mean by gain? I think we have that down. Ubiquitous decibel. I think we understand how to convert numerical gain or ratio gain to decibel using the 2 formulas. Well, 3 formulas technically if you want to get specific, but 2 of them are just the same formula with different inputs. Then we have understand what some arbitrary figure is telling us. I will
So
assume you
that's-
understand it.
that's the figure that where he's basically saying like, hey, your DC voltage is gonna provide your saturation limits for your
So our
amplifier.
rail voltages.
Yep.
All right, cool. So we understand that. Biasing the amplifier, or in other words, supplying DC voltage to make it work. That's also about rails.
Basically, you just have to do it.
Amplifier saturation. Another thing about rails. If if you're putting input signals that cause input signals plus gain that cause the output signal to bypass your rail voltage maximum, you will saturate your amplifier and it will simply spit out a straight line that looks stupid. No example problem on page 20. Does anyone know what that's referring to?
Yeah. So that's where
Yeah.
it's basically you're taking like you need to know that if you're given peak voltage or peak amperage, like finding your actual RMS voltage and current for your for the actually that are usable in the equations, and then after that it's basically just finding the gains and then using like doing a power balance.
So what is like page 20? What is that in a lecture? Is that in the book?
That's in the
It's in the
text.
book.
Okay, cool. Section 1.5. Know the simple amplifier types. Amplifier types, what is it? It's voltage, current, transconductance, transresistance.
Correct.
Yeah, it even says transconductance, transresistance. What is it? Transconductance is it's the opposite of resistance. So its gain would be G is equal to, if it's V equals IR, then it's I over V, right?
Yeah, it would be I out over V in for conductance.
Transconductance and transresistance is the opposite. You have V out over I in.
Yes.
Beautiful. Know the meaning of input and output resistance. I think we know what that means. Know example and exercise problems on various pages. I have a sneaking suspicion that may or may not be in our homework.
I will say so I've worked all the like example problems and some of the like all the homework from chapter 1 thus far at least, and there are some that are infinitely harder than any of the things.
Yeah. No, particularly because I finished all the chapter 1 homework, about half of the chapter 2 so far. That one where you had to design it and figure out like the best number of stages and which
Mhm.
I mean, it was entertaining, it was interesting, but it took like 2.5 pages. I'm like, what?
That
And
sucked up
it took me 2.5
afterward.
pages, and I don't even draw figures. I never draw figures unless it's like asked of me.
Oh yeah,
Yeah.
I worked on that problem for like probably a solid hour.
So if you know how to do that problem, you're set. Basically,
I winged it. It worked.
it worked.
Nice.
I don't know if I think I blacked out afterwards. So
User. All right. Then we
Yeah,
have
I guess that's something we haven't talked about at all because it wasn't on the test. Was the cascaded amplifiers?
yeah,
Although functionally, if
Oh,
you understand
functionally,
what the
it's
word cascade means, it's pretty easy.
yeah. I mean, basically, just know that that term. What is it? The like expanded gain, where it's like V out over VI times VI over VS. You're just like expanding that for the number of stages that you have.
Yeah. Then we have section 1.6, amplifier frequency response. See, I don't think we know this, but I also don't think it's going to be important on the test. I've seen it nowhere.
So he talked about it. That's like the time constant lecture he did.
Oh, so like with the capacitance, like reactance and stuff?
Yeah, for like RC circuits. It's like at the tail end. It's starting on page 136 on the textbook, and like there's no problems on it or anything like that. So I think it would at best be a conceptual question, but I personally don't really.
Yeah, I don't think that one will show up. Although I do think there's a chance this next thing shows up. Know what amplifier bandwidth is. So bandwidth is obviously what is it? Is bandwidth the frequencies that it can operate in?
yes,
Yeah. And that
Operate
like,
effectively in.
or
then
at
you-
least linearly, where if outside of it, it will.
Yes, I love when he says assume linearity.
yeah,
know what
and
they
that's
say
like the
about assuming.
upside down boat
Yeah.
plot.
Yeah.
And then what is it? It's like negative 3 dB down. Remember that? When that
Mhm.
happens, it's like stops working,
Is-
supposedly.
And ask is bandwidth and what was the flat? Oh, I can't remember the flat part. What it's called? Like, are they the same? And he's like,
Yeah, basically.
said yes, but no.
Essentially, yes. By definition, no.
And it's just like, oh, okay.
Yeah, I remember that. So you're in my section. You're a Tuesday.
No. I'm in section 2. I just watched the video though. So I'm
Oh,
physically.
so you watched someone ask that question?
Yeah, okay, I can see like the back of y'all's head, and sometimes I see someone sneaking stuff on their phone when they're in the lecture.
Oof.
It's hilarious.
Get wrecked person that he peeped their phone on.
Oh yeah, I
All
could.
right.
All I know that you were looking at your phone. You're probably just looking at the time. Let's be honest.
Yeah, then we have the single time constant, because we know bandwidth now, it's just the range of frequencies the amplifier operates in. Then you go with negative 3 dB down on either side of that bandwidth, and then you're going to drop out and it'll stop operating ideally and you're screwed. The single time constant network. There's a lecture somewhere about that, and he says it there, so.
Wait, say it again.
Single time constant network, STC network.
I'm
On RC and RL transient circuit.
Okay, maybe that's the time constant lecture he did.
Yeah. We'll just look over the lecture and say everyone should look over the lecture.
Yeah, I think for that it would probably just be like a true or false question.
Yeah, then we
because
have
that doesn't
Bode
show up
plots.
in any actual like calculation problems.
Yeah, then we have Bode plots that are not here, so cool. Know the summary on page 45 backwards and forwards. As we said earlier, if you memorize the summaries on chapter 1 and 2, you'll be set for all, probably all true false questions. And in general, you'll probably just have a better understanding of definitions and you'll be able to understand questions easier. Then we have, it says you just need to understand all the normal stuff, KCL, mesh, nodal, Thevenin, Norton, voltage division, current division, and phasor math. And this is chapter 1. Let's jump over to chapter 2. We need to know operations involving operational amplifiers. We need to understand common mode signals and common mode rejection, which we understand now. There are some exercises for that. Know one of the best examples of a common mode signal. Let's all say it. Noise.
sound. Well, noise.
Sure, sound. Why not?
What we all just made.
Yeah. Then section 2.2, the inverting configuration for op amps. Yeah. Make sure that power is headed to that negative terminal.
Yeah, and there's so like with the weighted summer, there's another example in the textbook where he's got like like you have basically it's like a I don't know what else to call it, but like a cascaded weighted summer.
That one, wait, does that mean
It's
he
like-
has multiple initial stages with multiple different outputs from several
So-
op amps into another one?
So it's like, let me see if I can find it. It's on the top of page 74. So it's like the first op amp has 2 voltage inputs going
Cool.
into it, and then that output is one of 3 inputs going to a second op amp. And it's not difficult to work. Like the math works out.
Wait,
the
then
same
how,
way.
so is it 2 summers?
Yeah, I think it's 2.
Then where does does one of the voltage sources, or is there just another voltage source as the other lead on the other
Yep.
summer?
Yeah, so
okay.
the second summer, the output of the first is acting as the input to the second.
So there's one op amp out and then the other one's just a voltage.
Uh,
For the other summer, if there's only one op amp with 1 V out, then there has to be another voltage source for it to be a summer, right?
yeah, I mean, well, like basically you have, yeah, so sorry, the first op amp has like 2 voltage sources coming in, like an arbitrary V1, V2.
Yeah, that makes sense.
And like, you know, the V out of that first op amp is going into the second op amp along with 2 other arbitrary voltage sources.
Okay,
And
yeah,
all of that combined is the like final VO of the.
Yeah. That
two-
definitely, that doesn't sound difficult at all.
No, like I would say look at like exercises D 2.7 and 2.8. They're like design problems where it's like, hey, design an op amp where the output voltage looks like this based on like the
Yeah.
figure given in the book. And like it looks like, I was like, God, I hope he doesn't give us one of these on the test. But then you like do the math and it's pretty straightforward.
Yeah, it looks like, as he says here, that the summer is probably important. So keep that in mind. It appeared on his old test. It'll probably show up on his new test. And I understand why, because in terms of analog logic and analog operations, it's definitely like a baller. So,
Mm-hmm.
so the next thing, entire section 2.3 is important, including follower. So isn't that just the varieties of implementations for them?
I think 2.3 is the non-inverting configuration where he goes through everything about the non-inverting op
Wow.
amps.
And the next thing is good stuff, the single op amp difference amplifier. So isn't this the opposite of the summer then? Or is this the differential, like the diffie-q one? No, it's not, because 2.5 is for integration differentiation. In my opinion, I only think the integration one's gonna show up. I know he's talked about that one more. And in general, I think integration's cooler than differentiation.
Yeah, so this one, the difference amplifier, you have 2 input voltages rather than like on pins 1 and 2, rather than one of the inputs being connected to ground.
Mm.
So it's
So you
like
have 2 different voltages, so it's just doing the whole common mode gain. Subtract
so
one
you
voltage
have
from
a neg-
another.
yeah, you have a negative feedback loop on this one, but then yeah, like pin 2 just has like the textbook definition of like a figure 2 difference amplifier. The positive pin of the amplifier has a arbitrary input voltage and then 2 resistors before it goes into the second pin on the
Nuts.
amplifier.
All right. Then he says omit. Then we understand the integration, and differentiation is probably just the opposite of that. Well, it's not probably, it definitely is. Section 2.6 is an omit. And then yet again, he says know the summary. So everyone memorize your summaries. And then do homework. So we've covered all of that. So that's cool.
Yeah, I feel like for especially chapter 2 is like, as long as you know those like 5 assumptions that you can make with the ideal, like you're going to apply those to probably everything. And then it's just different like circuit analysis techniques to figure out everything around the op amp.
I'm excited to do the power supply stuff because power supplies are great.
Like you're talking like the stuff we're getting to now and
Yeah, the next stuff.
Yeah, it'll be pretty interesting, I think.
Yeah, but the funny thing though is I like the concept of it, but being the plebeian I am, I literally just use like the IC voltage regulators for everything to get me a 5-volt line off of a 9-volt battery. Wait, no, that's is it 5 volts? Wait, am I frying
so.
everything?
Oh no.
I have to look at this right now. Is this supposed to be 5 volts or 3.3? Oh hell. Wait,
At this moment, Ethan knew he
Wait.
fucked up.
He just went through his midlife.
I need to find. I'm turning on my multimeter. I need to know something really fast.
Do we think he's gonna? I hope to God not that he's gonna put anything like for that symbol convention on there, like with
I
like
hope
the
not.
lowercase I, big C,
Oh,
small c,
okay,
all that crap.
it's when you really look into it, it's not too crazy.
Which symbol convention is he talking about? Like that one table with all the things?
No, it's like a graph of like a sinusoid where he gives like all the differences between what like lowercase I subscript
Oh, like one of them's
capital
measured
C.
from one's
Yeah.
measured from 0, one's measured from the median.
Yeah.
I don't know if we need to.
Yes, right there.
Yeah,
Yeah, that one.
that's the worst convention
Yeah, it
I've
sucks.
ever seen.
I don't think I've
any
used it. I
college
don't think
class
I've used it
taken.
once. I don't think I've used it once, honestly, and I don't think I ever will.
It wouldn't be as bad if it wasn't for the fact that C's look literally the same capitalized or
Oh
not.
God, yeah,
Like if it's
it's terrible.
R or
E.
just or an A or just something that was different, but no, it has to be C where it literally looks exactly the same.
Yeah, kind of cringe. Kind of cringe.
Then a J, then it had a dot. You know, it's just whatever.
C and X are about the worst two you could use.
Yeah,
Yeah.
and if you look at like the reasoning the
O.
textbook gives
Yeah.
for like what lowercase subscripts versus uppercase subscripts mean, it's so stupid.
Mm-hmm.
It's so stupid.
They just say it is what it is.
Basically.
Yeah, all right. So that's that. So that sounds like everything. So hopefully, this video and everyone who attended will be able to pull, solid 70, 80s on the test with ease. And if they grind hard and have no friends, they might get an A.
Maybe.
Okay, I
Do
feel
we-
attacked.
I am attacking. That's what I do. I mean, the sad thing is I intend to do the same. So it's.
No, I'm gonna do my best, but yeah.
Now for the homework, what did he specify? Are we having to turn it in on the test day still?
He has not specified
So
anything
he-
other than there
So
would
he
be a
just
sign sheet.
Yeah,
he
he
did
sent a
specify
Canvas
some stuff. So he
message.
just sent something where he said, because we were asking about it and we emailed him today, and he said he's going to tomorrow post the certification sheet, right? He's not big on electronic submission, so he's not going to have us scan them in, allegedly, because he didn't mention it at all. He's not going to have us scan in our worked assignments. He's simply going to have us put our initials on the certification sheet and turn that in, scanned wise probably through email on Thursday. So
He's
theoretically, someone could just not do any homework and
Just initial it.
just lie. But the thing is,
So we're good, Noodles. We don't
yeah,
lie.
we're good
Already on
noodles.
the test, they'll be screwed.
yeah, I
Yeah,
was gonna
we're-
say, like, I feel like he'll know they didn't do the homework when they get like a
Well, the
6
thing
on
is, here's the thing. So at the end of the day, like, it's not like when people finish their homework, they go and burn it. So at the end of the
Yeah.
day, for now, he could have it just be, oh, credits here for now or whatever, and then take the credit away later if it turns
That's
out
true.
that you were lying. So best policy, don't lie.
Best policy. If I was him, I would just collect it. It's not like he actually has to grade it. He could just say
No, I don't
he's
think
grading
I don't
it.
think he no, I don't think he ever intended to grade it. I think this
Well,
was
that's what he normally does.
this was always for completion, I think.
Yeah,
Well, I mean,
but-
yeah,
you
but turn it
normally
in so at
do
least you
what
know
we had
who's
in the
doing it.
original syllabus is we just have the submission sheet that we paperclip or staple on top of our homework that we turn in, and he doesn't even look at the homework. He's probably just like skims through like, oh, okay.
Yeah, but I feel like for that, it's like if he ever wanted to, he could like
could.
catch you for lying. So why would you even risk
Yeah.
like the
Exactly.
minimal effort it takes to like even just like if you're like work the problem and it's wrong and you're like I like literally right I don't know, you at least attempted it, you know?
Exactly. There's
I'm
no
a master. I'm a master of writing I don't know on exams for like one problem every single time.
I actually got points on my proofs class for posting a meme because I literally did not know.
That's what I like to hear.
What'd you do? What'd you put in?
Oh, if you check the group chat real quick, I will show you exactly what I did.
All
right.
So is there who's gonna actually be in class in person on Tuesday?